Welcome to this explainer. Today, we're going to completely demystify organic chemistry by exploring the incredible architectural system of carbon molecules. You can kind of think of this as your masterclass in the ultimate building blocks of life itself. We're going to see exactly how carbon forms the foundation of literally everything, from the food we eat to the medicines we take. And we'll look at how we can actually read, draw, and even tear down these microscopic blueprints. So, let's kick things off with a pretty wild piece of scientific history. Did you know that for a really long time, scientists firmly believed that organic matter possessed this mystical, vital force? Yeah, it was a mainstream theory called vitalism. The whole idea was that organic compounds could only be created by living things. Basically, they thought there was some special, untamperable spark of life inherent to them, and they could absolutely never, no way, be synthesized by human hands in a lab. But then, in 1828, one guy basically shattered that entire worldview. Enter Friedrich Wöhler. He was a brilliant German pioneer in organic chemistry, and he went completely against the grain of that mainstream vitalism theory. How'd he do it? Well, he actually synthesized urea, a totally known organic compound, directly from an inorganic compound called ammonium cyanate. With just that single groundbreaking experiment, Wöhler proved that carbon's architecture could actually be built by human hands. He proved the rules of chemistry apply universally, and honestly, that opened the floodgates to the millions of organic compounds we've synthesized ever since. So, here's our roadmap for today's explainer. We're going to start with the carbon chemistry revolution, then look at classifying organic compounds and the IUPAC naming system. After that, we'll cover visualizing molecular blueprints in 3D, dive into the wild world of isomerism, and finally, analyzing the elements. Let's get right into it. Starting with Section 1. The carbon chemistry revolution. This is all about why carbon is the ultimate structural material for life on Earth. The real secret behind this whole revolution, it basically boils down to one absolute superpower: catenation. See, carbon has 4 valence electrons, which means it really wants to form 4 covalent bonds to become stable. And because the bond between 2 carbon atoms is just incredibly strong, carbon has this unique, amazing tendency to link up with itself. It forms these massive, continuous chains and rings. This property, catenation, combined with having those 4 connection points, makes it an infinitely versatile building block. It's not just violently losing or gaining electrons like in ionic bonds. No, it shares them, building these incredibly stable, complex frameworks that literally hold our world together. Moving right along to Section 2, classifying organic compounds. Because with millions of possible carbon structures out there, we definitely need a way to categorize all this microscopic architecture. Think of the main carbon chain as, say, the blank walls of a building, and the functional groups as the doors and windows. A functional group is just a specific combination of bonded atoms that dictates exactly how the molecule is going to react, totally regardless of how long that main carbon chain actually is. For instance, if you attach an OH group, boom, you've built an alcohol. It ends in -ol, like ethanol. Or if you attach a carbon that's double bonded to an oxygen and also to a hydrogen, you've suddenly got an aldehyde. These functional groups are essentially the active sites. It's where the chemical magic actually happens. Which brings us to Section 3, the IUPAC naming system. Think of this as the strict universal address system for the microscopic world. The International Union of Pure and Applied Chemistry, or IUPAC for short, gives us these 4 straightforward steps to build a perfectly logical name for literally any organic molecule on the planet. Step 1, you find the longest continuous carbon chain. That gives you your root word, like meth if there's 1 carbon or hex for 6. Step 2, you number that chain, but you do it from the end that gives your attachments, or substituents, the lowest possible numbers. Step 3 is identifying those attachments as prefixes or suffixes. And finally, step 4, just arrange those multiple substituents alphabetically. It's like a giant puzzle. By combining a prefix, a root word, and a suffix, chemists literally anywhere in the world can pinpoint the exact structure of a molecule just by reading its name. All right, on to Section 4, visualizing molecular blueprints. How do we take a complex, 3-dimensional building and draw it accurately on a flat piece of paper? Well, chemists have developed some pretty clever conventions to show 3D depth on a standard 2D surface. First, there's the solid and dashed wedge formula. It uses a thick, solid wedge to show a bond popping right out of the paper at you, and a dashed wedge for a bond fading back into the background. Then we have the Fischer projection. This one puts the molecule in a cross shape. Horizontal lines are coming towards you, and vertical lines are moving away. There's also the sawhorse projection, which looks at the carbon-carbon bond from a slightly diagonal, elongated angle. And then, my absolute favorite, the Newman projection. This is where you look straight down the barrel of a carbon-carbon bond. You view the front carbon as a dot and the back carbon as a much larger circle. It's a real game changer for visualizing these things.
And here's why we actually need all those fancy drawings. Just look at this physical ball and stick model of methane. Because of a phenomenon called sp3 hybridization, which is just a fancy way of saying the atom's electron orbits mix together, the center carbon pushes its 4 hydrogen atoms as far apart from each other as physically possible. This creates this beautiful 3D tetrahedral geometry. So physical tools, whether they're ball and stick, framework, or space-filling models, are absolutely vital. They help us truly perceive the actual spatial reality of the organic world.
Let's transition over to Section 5, the world of isomerism. This is where organic chemistry gets truly mind-bending. It's the idea of taking the exact same materials but building entirely different structures. Now, there is a super important distinction between the two main types of isomers here. You see, both have the exact same molecular formula, meaning the exact same number of carbons, hydrogens, oxygens, the whole shebang. But with constitutional isomerism, the atoms are actually wired together differently. They might have a totally different carbon chain skeleton, or maybe a functional group gets moved to a different spot. On the flip side, we have stereoisomerism. This means the atoms are connected in the exact same sequence, but, and here's the kicker, they're pointing in completely different directions in 3D space. This includes geometric isomers, where you might have bulky groups locked on the same side or opposite sides of a double bond. And that simple spatial change, it drastically alters the molecule's stability and properties. Pretty wild, right? Finally, we reach Section 6, analyzing the elements. If the previous sections were all about being an architect, this section, it's all about being the building inspector. We're going to tear the molecule down in the lab to figure out exactly what it's made of. So if we want to know exactly how much carbon and hydrogen are hiding in a sample, what do? We burn it. We literally take a precisely known weight of our organic substance, put it in a combustion tube with some copper-2 oxide, and pass pure, dry oxygen right over it. The intense heat and the oxygen completely oxidize the sample. The carbon turns into carbon dioxide gas, and the hydrogen turns into water vapor. We then push those gases through an absorption apparatus. The water gets trapped by sulfuric acid, and the CO2 gets trapped by a strong potassium hydroxide solution. By simply measuring how much weight those specific traps gained, we know exactly how much gas was just produced. Once we have those gases trapped, we can use this beautiful little formula to calculate the exact percentage of carbon. It's pretty straightforward. 44 grams of carbon dioxide contains exactly 12 grams of pure carbon. So we just multiply 12 over 44 by the weight of the carbon dioxide we captured, which we'll call Y, then divide that by the original weight of the sample, W, and multiply the whole thing by 100. It's just an incredibly elegant way to work backwards from the combustion ashes to uncover the exact elemental percentage of the original molecule. But hey, what if there's nitrogen hiding in that architecture? For that, we usually turn to Kohldahl's method. This one is heavily used in testing everyday things like foods and fertilizers. Basically, we take our organic compound and aggressively heat it with concentrated sulfuric acid. This violent reaction quantitatively converts any nitrogen present straight into ammonium sulfate. Then, through a clever process of adding strong alkali and distilling the liberated ammonia gas into a standard acid, we can use a back titration calculation. That tells us the exact amount of nitrogen that was hiding in our original sample. Now, if we need an even more precise technique for tracking down nitrogen, we turn to the Dumas method. Instead of using sulfuric acid, we heat the compound with cupric oxide in a really strict atmosphere of pure carbon dioxide. This process breaks the compound down and yields free nitrogen gas. That gas then travels into a specialized piece of equipment called a Schiff's nitrometer. The carbon dioxide gets absorbed by a potassium hydroxide solution, which just leaves the pure nitrogen gas to collect right at the top. By measuring the exact volume, temperature, and pressure of that collected nitrogen, we can flawlessly calculate its percentage in our original organic building. To wrap up this explainer, I want to leave you with a thought. Look around your room right now. Your clothes, the wood in your desk, the plastics in your computer, the food in your kitchen, even the DNA in your very own cells. How many of those materials contain this exact same hidden architecture of carbon? Well, the answer is practically all of them. By understanding things like catenation, functional groups, 3D geometries, and laboratory teardowns, you aren't just learning chemistry, you're literally learning the source code of the physical world. Keep looking closely at the world around you, and I'll catch you in the next explainer.